Okay, so I hope midterm preparations are going well. So today we're going to look at the frequency response of various CMOS op-amp stages, from the current mirrors to telescopic and folded cascode, what compensation issues, and then we're going to sort of do the Miller compensation of the two-stage, if we get to it. So just looking at our basic structure, so let's say diff pair with current mirror. It's useful to analyze kind of what the mirror actually does to the frequency response of the amplifier. So we have something like this. And then we can say, doesn't matter, we'll just label this I tail, because we really want to see what's happening in the top part of the circuit. And let's label this as M1, M2, M3, M4, and then you can say, okay, this node I'm going to label X, and this node I'm going to label Y. And so if we look at these two nodes, there's going to be kind of like a lump cap here, Cx, that is going to represent kind of the capacitance of M4, of M3, of drain caps of M1 and M3, etc. So there's quite a bit of connections that are different devices that are connected to this node. So that definitely will have some larger capacitance that will get introduced here in the mirror. So if you, for example, itemize, we can say it's GS3 plus GS4 plus CDB3 plus CDB1, right? Okay. Now, if we go and write a small signal model, let's say if we ignore ROs, that we said that last time when we analyzed the current mirror, if we do this to the first order, we can assume that the bottom is symmetric, right? Because I just have two sources, and one of them is GM1 VGS1, another one is GM2 VGS2, and then I just have VID over 2, and then here minus VID over 2. And then what I have at the top, now in this case, instead of just having 1 over GM3 that we had previously, I also have this CX. So we're just going to lump it together with that. And then we're developing a voltage here. Let's do it like this. VSG4, and then we have a source that is grounded, which gives us GM4 times VSG4. So I'm ignoring the R naughts, but I just want to see what the transconductance is. So for that, I have my IO here, and I'm shorting the output. Obviously, this is the output over here. So again, we have I down and I up. So if we want to calculate the GM, GM would be this IO over VID, because we're applying a differential input. And then IO is I up plus I down. And in this case, if we look at the I up, that's minus GM4 times VSG4. And then VSG4 we can express from this side over here as GM1 minus GM1 times VID over 2 times 1 over GM3 in parallel with 1 over SCX. Right? And then we have, so all this essentially is I up. And then we have plus for I down, it's just GM2 times minus VID over 2. I think I have one minus extra. This minus is not there. Okay, so when we take a look at this piece, it's really two conductances, GM3 in parallel, so it's really GM3 plus SCX. And if we write IO, we're going to get minus GM1 times 1 over 1 plus SCX over GM3 plus GM2. And all that times VID over 2. Here we're assuming that GM3 and GM4 are matched, so we can cancel that out. When we pull GM3 outside of the, so assuming GM3 equals GM4, and then GM1 equals GM2. Right? Okay, so from here, if we now assume GM1 equals GM2, we can pull out GM1. So we're going to get GM1 over 2 times, and then here 2 plus SCX over GM3 over 1 plus SCX over GM3. And then that is equal to minus GM1, and then we have sort of the familiar expression 2 GM3, and then 1 plus SCX over GM3. This is of the form, this should be of the form 1 minus S over 0, 1. This is the form 1 minus S over pole 1. So we have a pole that is equal to GM3 over CX, and then we have a 0 that is equal to 2 GM3 over CX. So this mirror essentially introduces a pole 0 doublet or pair, and you see that the distance between these two is only 1 octave. It's only 2x difference. So if you go and now analyze what's happening with so this is GM. If you see what's happening with GM for very low frequency versus very high frequency, at very low frequency, this whole piece is gone. So So we're going to have this, which is kind of what we know already about the current mirror diff pair. But at high frequency, you know, if j omega or S is really high, then these ones don't matter. So you'll just get GM3s will also cancel out, and you're just going to get GM1 over 2, or minus GM1 over 2. Okay. And if we look at the frequency characteristics of GM versus omega log, that means that there is a pole 1, and then a 0, 1. And then what happens is you're at GM1 here, and then you start dropping at the pole, but very quickly 0 flattens at GM1 over 2. Because you're only moving by an because these two are only 2x different, then this difference is also 2x. Because you're going 20 dB per decade, or 3 dB per octave, 2x per octave, right? So this is minus 20 dB per decade, or minus 3 dB per octave. Of course, if you look at the phase will just, so the phase is going to be 0 up until here. And then here it's just going to do a little start going down because of the pole. But then because this is a left, so this is left half plane 0, it will start going back up. We know at poles, so when you're past the pole, your phase is down by 90 degrees. When you're past the 0, left half plane 0, your phase is up by 90 degrees. Right? So you just start coming down because of the pole, and then you come back up because of the 0. And the depth of this dip is something like minus 20 degrees. Okay. So if you go back here, at high frequency, S is very big, right? Or j omega is really big, right? So this component starts being a lot bigger than 1 in magnitude, right? If we were to do the magnitude of this, it will be 1 squared plus omega Cx over 2 GM3 squared, right? And so then this will cancel with this. So Cx and GM3 will all go away, and you're going to only get like 1/2, and then you have GM1 over here. Okay. I mean, if we take a look at the previous diagram, of course, we can, from here, we can always, ignoring the 0, we can always find what the pole is, right? How can we do that very quickly? Anybody tell me immediately what the pole is? How would you do that? You can look at this and tell me immediately, or you can look at this piece over here and tell me. If I'm just looking for one pole, what do I do? How many capacitors do I have in this circuit? Only one right now that I drew, right? So what does that capacitor see in terms of the resistance? Yeah. So open circuit time constant. I'm assuming that this Cx is bigger than anything else. because it's kind of a sum of a lot of transistor parasitics, and in the other places I have only one or so. So then I'll keep everything else open and just look at what it does. The inputs are going to be at 0, so these sources are dead. And even if I had RO like hanging off of here, this resistance is a lot smaller. So what CX sees is just 1 over GM3. So my pole is just going to be minus 1 over GM3 times CX. And then that will be really just minus GM3 over CX. Notice this should be minuses here. So this is left half plane. Okay, so notice that's the same exact answer, right? And so if we take a look at what GM3 CX is, so pole 1 is minus GM3 over CX. I don't know why it's doing that. So CX is approximately 2 CGS. Okay. Because it's CGS3 plus CGS4 plus some little junk. So with this, P1 is equal to minus GM3 over 2 CGS3. So it's approximately minus omega T over 2. Yeah. So, and 0, again, we said that 0 is going to be twice that, right? So 0 is approximately at omega T. Right, so, yeah. Yeah, because M3 equals M4 for the mirroring, right? So this is just to give you an idea where they are, right? Because normally when we start adding other components, we're going to have, for example, the output pole in the 2-stage will be kind of, the most dominant pole will be way below this. This is kind of around the FT and FT over 2. But as in some configurations where we're pushing the unity gain frequency close to that, they can start playing a role as a third pole and another 0 that sits right next to there. So in configurations where you have these single-ended differential pair structures, you sort of need to start worrying about this kind of as a third pole, especially in Miller when second pole starts shifting, so this doublet starts playing a role. Okay. We're going to sort of start revisiting now the cascode stages, just because they're kind of simpler to understand how to map compensation to, and then we're going to look at the 2-stage. So I'm going to first do the compensation of single stage. CMOS, and then, okay, let's say under A, we'll do the telescopic first. So I'm going to do a little bit of a simplified schematic here, fully differential, just because I want to avoid these current mirror pole and 0 that I just talked about. But we already said that they're kind of further away, so are not going to affect the story that much. So we said then in the, I'm just going to do, OK, here. So we're doing a fully differential version here. Bias. And our outputs are going to be right here. And in this simplified thing, we're just going to say that all the parasitic capacitances are going to be lumped into sort of a D output, CL, and then this node over here. We're going to call it CP. And so this is VI plus, VI minus. I can label this as VO plus, VO minus. The gain can be negative in this, as it is in this case, from VI plus to VO plus. So since this is fully differential, we can, for differential input, we can have a half circuit, right? So we will ground this node. So we're going to get, so say M1, M2, M3, M4. So we get something that's kind of a familiar situation that we derived last time when we looked at two-stage amplifiers. Oh, sorry. This is going to be like this. And then here we have CL. And then on this node, we have VO D over 2. CP in this case is, for example, CGS 3. So that's this capacitance over here because gate is a ground, so like this cap. It's also CDB1 and CSB3. Right, but it's approximately CGS3. So if we take a look at this, how many, if we're really lumping all the parasitics into CP and CL, how many poles do you think we're going to have? Two capacitors, independent, how many poles? 2 poles. Okay. And when we have 2 poles, we know we have 2 poles. How can we analyze both of them? How do we find both of them? Exactly. Okay, so which one for which? First and what is first and what is first dominant or non-dominant? Okay, so P1 dominant. Right. We're using open circuit time constant because we're assuming it's dominant, so the other capacitor hasn't activated yet, hasn't shorted yet, right? So that other capacitor can only contribute by, if you're looking at the resistance that the dominant capacitor is seeing, so then this other capacitor should be open during that time, right? Okay, so from that, what is P1? It's -1 over our dominant capacitor here will be let's say CL, times what? What's the resistance that CL sees while CP is open? Yeah, so it's seeing the R out, right? So I'm going to say, and R out is, let me just write it better. So R out will be right, approximately. It's just like cascode output resistance, right? Okay. And then we use short circuit time constant for P2. So now we're analyzing the impact of CP. This is P1. But at that time, we're assuming that the output is shorted by CL. And so what resistance does then CP see? Yep. So it's seeing 1 over GM3 times CP. RO3 is kind of lumped in parallel with that, as well as RO1, but we're neglecting those two, right? Because those should be way bigger. So if you remember, CP was just CGS3. So this is approximately minus omega t. And this is actually one of the kind of benefits of cascode amplifiers, as we said in the last lecture. Yeah?
For CP, why don't we consider the
Gate drain moment, good question. So, well, CP is viewing it so that, VID is kind of a source here, right? So CGD is always much smaller than CGS, right? And the only case where it really comes into action is through the Miller effect, right? Because then you're multiplying by GMRO, so then it can start being comparable to CGS and maybe even dominate, right? But in this case, you're sort of driving from drain. So you just see CGD, and it's not as big. Yeah?
What's the physical significance of omega t? Why is that good? That's what we got.
So omega t, you remember when we did the derivation, that's kind of the current unity gain. After omega t, you stop amplifying current through the transistor, right? You start shorting the transistor through the C, and you don't get any more current gain. So it sort of signifies how fast can signal go through the transistor and still do something. Right? Okay, so this sort of shows you what the benefit of the cascode is, that it introduces a second pole, but the second pole is kind of very far away. So potentially, when you do in the feedback configuration, you can kind of extend the closed loop feedback all the way to omega 2. Okay. If we look at these two, P1 is actually much smaller than P2. And the reason is that R out, which is equal to, approximately GMRO squared, is obviously much bigger than 1 over GM. And then also, CL is greater than CP. So both of these kind of provide for larger separation between the two poles. If we go and draw the frequency characteristics, and the angle, this is just a two-pole system, right? So what is going to be my phase margin? Will depend what my feedback is, right? But in other words, can it ever be negative? I have only two poles. So the first pole drops the phase down, and then another pole will drop it another 90, right? This is approximation. Obviously, it really is going like this, and then this one is asymptotically getting to minus pi, right? So regardless of where 1 over f curve is, right, I'm never going to cross at the point where I'm actually touching minus pi, right? So my phase margin is always positive. So. Okay. So how do I do compensation here? This one is defined by CL. This one is defined by CP, parasitics, right? So by adding more CL, which is kind of the narrow banding that we did, I can, in a separate fashion from P2, move P1 to the right place. And why do I want to do that? Well, for some 1 over f, let's say maybe for this one over here, I'm past the pole, right? So, my phase margin is not really good, maybe 30 degrees, okay? And we saw that you do get some peaking there, and you may not like that because your settling time is going to be affected. So you may want to have a 60 degrees phase margin or something, in which case you do want to cross before P2 or at P2 for 45. So that means that your pole will have to move to here. And so here you're going to have CL prime. So you're going to have to add some capacitance to the output of the cascade in order to be able to compensate it well. Okay. Let's take a look at another one, another flavor, which is the folded cascade. I sort of mentioned last time a little bit what the trade-off there is, but let's do it kind of explicitly. In a folded cascade, we have a very similar situation. Because after all, small signal models are very, very similar. So we have the inputs, and then we're stealing part of the current. The P cascade, and then loaded by I2. I'm going to take this. And then this is V bias. And these are the outputs. Okay. Just like we did in Cascade, we're going to have some load that's both from the devices as well as kind of whatever we're attaching to the amplifier. So some CL at the output. And then at these two intermediate nodes, we're going to have CP prime. Labeling it CP prime simply because it's actually not exactly the same as in the cascode case. In this case, actually, CP prime is bigger, sometimes much bigger than the parasitic capacitance that we had in the previous case. And there's a few reasons for that we're going to list shortly. So if you take a look at this, again, the half circuit is very similar to the cascode. Now here we have CP prime, and then we just feed this guy into CL. And on this one, we get VOD over 2. So again, open circuit time constant. P1 is minus 1 over R out times CL. Short circuit time constant, P2 is minus GM. Okay, let's label this M1, M2, M3, M4 over CP prime. Now, since CP prime is greater than CP, P2 folded cascode is going to be smaller than P2 of telescopic cascode. This is the case here because we have more devices. Cascode node. Notice that I have a current source now plus the, and obviously these are some devices, at least a drain that is connected there of the current source. Plus I have now the interconnect that has to go from N to P, and then I have a P device. And as well, if I'm trying to keep GM3 the same in both scenarios, I will need to have a larger, because my KP is smaller, I have to have a larger W over L. Right? So W over L 3P has to be greater than W over L of 3N for same GM. Right. So this, again, will also increase the capacitance. So kind of all is working to decrease the second pole of the folded cascode. So if you look at the characteristics that we had over here, your unity gain bandwidth, meaning where you want to cross the 1 over F, is going to be, you always want it to be sort of below P2 just to get a reasonable margin. So if P2 is lower in one design versus another, then your unity gain will be lower in telescopic, for example, than the, in folded than the telescopic, because P2 is lower. So your unity gain is sort of tied to P2. So in folded cascode than telescopic cascode. Now, we said that adding a current mirror to turn this into designs I showed you last lecture, like single-ended designs. So single-ended. You need to add current mirror pole and 0 at omega t over 2 and omega t, right? And now you see, I mean, this is kind of getting close to what our pole 2 originally was, right? See, in telescopic, our pole 2 was around omega t. And now if we add a current mirror, we're adding sort of another pole right there. Or actually, one pole early, half at omega t over 2. So a bit earlier, plus a 0 exactly where this pole is. Right? So then we're moving, by adding a current mirror, we're actually also shrinking the unity gain, because now that pole from the current mirror becomes more dominant as a second pole than this one that we had over here. Right. Okay. If we take a look at another flavor that we discussed last time, and that's, we had.
Can you draw the Bode plot for when you add the current mirror?
For which one?
When you add the current mirror. I'm confused.
Okay, good, thanks. So if you look at A, right, if you add the current, so what happens before you have a current mirror, right? You have pole 1, which is kind of dominant. This is kind of what's set by the output and big R out, right? And then you're going, and your pole 2 is kind of almost at omega t, right? So this is P1, this is P2, this is omega t. Okay. And then if you add the current mirror, now you've added a pole. Let's say pole 3 is at minus omega t over 2, and then 0 is at minus omega t, right? So now you're adding a 0 exactly here. So that pole and that 0 cancel out. And then you have your new pole kind of half shifted down by 2x. So this is your pole 3, right? So if you draw the new phase margin, right, it essentially drops here by 90, and then around pole 3 drops by 90, rather than extending over here and then dropping here by 90, right? So we said that, so since this is canceled, now this is my new pole 2, right? And we said that in compensation, everything is going to be with reference to that one, right? Especially in cascode, because I'm now moving pole 1 in cascode wherever I want, because it's kind of independent. Pole 1 is CL dominant. This one is sort of CP dominant, right? So I can move this one independent of pole 3 or pole 2. And in that case, all the phase margin is now with respect to P3. Right? Where I want to cross, well, if I move this guy, I want to cross somewhere. So if this is my 20 log 10, 1 over f. I want to cross somewhere earlier than this P3, because then I get better than 45 degrees phase margin. So in this case, because P3 is half of what my P2 used to be, yes, I get half smaller by half unity gain bandwidth, right? Okay, thanks. That's a good question. So I think I drew, okay. In an active cascode, we had this situation. I'm just going to draw one little piece. Okay, but you saw that in telescopic we had like 4 guys like this. We had two A1s on each branch, and then we had 2 A2s on each branch, right? was lecture 23. Yeah, so these were the amplifiers, and this, we had this situation over here, right? And so each one of these guys actually has to be stabilized, because it can have 2 or 3 poles or 1, 2 poles. Even if it's 2 poles, just from the mirror and then the dominant pole set by the output, you're still going to have to stabilize it to in order not to have very low phase margin, right? So with that, the way you're going to do it, just like we discussed here. So this is going to be kind of some CL that you add to this piece over here, whether you terminate to ground or maybe minus VSS over here. Each of these will be sort of separately stabilized in the loop. Okay. Let's start with two-stage CMOS, and we have a couple more minutes before we finish. So, just going to draw our standard. M1, M2, M3, M5, M6, M7, V bias. Minus VSS. And then we're taking the output from here. Now we can say this is VID over 2 minus VID over 2 VO. Sorry, this is minus, plus. Okay, so if we take a look at this, we can draw sort of the simplified small signal diagram. VID is here, and then I have GM1 times VID. If I look at sort of the first stage, I have my output conductance is RO2 in parallel with RO4. So I'm now sort of drawing, this is kind of the GM1 times ROUT1, right, for the, and ROUT1 for the first stage amplifier. I'm not drawing transistor small signal models, but I'm drawing amplifier small signal model, right? Now, this is the same as we said, the amplifier can be represented with GM, V in, and then R out, right? So we know already what the answer is for these two for the current mirror one, right? And then what I have is some capacitor, C1, that's kind of on this node over here. And then I can add here a capacitor C. That's originally from CGD, but I will like to add a capacitor there, like we talked about the Miller compensation, we did it for bipolars, in order to see what the effect of this guy is. I'm going to be on poles in the circuit. And then I have C2 from the output. And then, of course, from M5, there is GM5. So this is going to be, okay, say here, GS5, or let's label it VSG5. And then we have, again, our RO5 in parallel with RO6. And this is VO. Okay. So if you look back what we did for when we analyzed two-stage amplifiers and the impact of this, just regardless whether it was CMOS or not, we sort of had exactly this same situation where we had three caps like this, and R from the previous stage and R from the second stage. So if you looked at the transfer characteristics, it looked something like this. In DC, gain was GM1, RO2 in parallel with RO4. We know that, times GM5, RO5 in parallel with RO6. And then that divided by two poles. And there was a 0. Right. So if you take a look at the effects of C, let's say, if C equals 0, what happens? These two are separable, right? So I can analyze this part of the circuit completely separately from this. So there's no influence between the two poles. I'll have pole 1 will be determined just by the RO2, RO4. So we're going to call this R1. And then pole 2 will be just determined by RO5 and RO6. I'll call this R2. If C goes to infinity, however, it's starting to short the gate with the drain. Right? So now these C1 and C2 start interacting with one another. Right? And in the ultimate case, where C is so big that it effectively shorts these two, then we just have the gate voltage sitting across the source. So this becomes a resistor. It becomes 1 over GM5. Right? And so then now our pole 1 is going to be, pole 2. So pole 1 is just from this, if you look at the Miller effect from CC, it's going to be 1 over RO2 in parallel with RO4 times C1 is going to be negligible, but C, which is amplified by 1 plus GM5, RO5 in parallel with RO6. So this is Miller. So this is going to go to 0, right? Because C goes to infinity. Pole 2 will be what I said, determined from these two capacitors and whatever the resistance comes from 1 over GM5. So it will really be GM5 divided by C1 plus C2. And yeah, that's that. So if we take a look at this P2 versus